Hello and welcome. My name is Bianca Coop, and I will be your host for today. Welcome to today's webinar, an IoT case study on how to address wireless connectivity. This webinar will be recorded and available on demand for future reference. Throughout this presentation, please submit your questions using the panel on the right-hand side of your screen, and we will address these questions at the end of today's presentation. As we move forward onto the next slide, I will go over the agenda for today. Today's agenda will cover the speakers and a company introduction for both TE Connectivity and Exelonix, an IoT platforming use case addressing wireless connectivity challenges and their solutions, and the real-life case implementation results and key takeaways to reference. As we move forward to the next slide, our first speaker today is Christian Koehler. Christian Koehler is the Senior Manager of Product Management for RF Antennas for TE Connectivity's Data and Devices Business Unit. Christian's primary focus is on creating and enhancing sustainable and competitive momentum and being a competent and agile partner to our customers. Christian has a background in the semiconductor industry and has worked for TE Connectivity for over 30 years, with various roles throughout the organization, from sales to product management for automotive, consumer, and datacom industries. Christian has an engineering degree in microelectronics from the University of Chemnitz and is also Green Belt certified and holds multiple patents. As we move forward to the next slide, our second speaker for today's webinar is Matthias Sega. He is the Managing Director and founder of Exelonix. In 2013, Matthias was one of 4 founders of Exelonix, a company that delivers wireless IoT devices and services to B2B customers. Exelonix provides solutions for sensing and monitoring, track and trace, as well as medtech applications. Mr. Stege has co-founded Signalion, a vendor of LTE station test equipment. As part of the Signalion management team, he has acquired major leads such as Ericsson, NSN, Huawei, Alcatel-Lucent, as well as with operators of Vodafone and DTAG. In 2012, Signalion was sold successfully to National Instruments. Currently, Matthias graduated as a PhD at the University of Technology from Dresden and holds a diploma in electrical engineering and a PhD in wireless communications network. We hope you enjoyed today's presentation, and without further ado, I invite Christian to continue today's presentation.
Hello, everyone. Let's first introduce both of our companies. TE Connectivity is a almost $15 billion global company for interconnect technologies divided into 3 segments. The biggest one, transportation, with 9 billion. The second one, industrial, 3.8 billion. And communications, with $2.1 billion annual sales. Where we are coming from, we belong to the communication segment. And the amazing amount of 247 billion products are manufactured on an annual basis. TE is spending a lot for engineering, for getting into a holistic approach. As a result of our 15,000 plus patents granted, for pending the huge amount of 610 million is paid on an annual base for engineering, for research and development for 7,500 and more engineers, which are split globally, and approximately 20%, a fifth of our annual sales is related to new products. Let's dig a little deeper into the IoT antenna facts part of the data and devices business unit. TE Connectivity has designed, manufactured, sold and shipped over 1 billion antennas globally so far. We have been introduced to the development, prototyping and manufacturing of antennas since smartphones or mobile phones and wireless wearable devices exist. And TE offers not just a broad range of catalog products, but also design service to provide world-class RF performance. As an example, recently there was a challenge to develop a combo antenna for narrowband IoT, Cat-M1, GNSS, Wi-Fi, and Bluetooth for an entire family of tracking devices. And analyzing the use case, it turned out that the use case is pretty challenging for antennas, since the tracking device need to be installed on a metal container, so big metal plate. And we managed that the device was still able to connect seamless to all before mentioned services. And on top of this, the first round of certification passed. The device could service multiple regions. Initially, there was an intent to have a device for the American market, another device for European market. It's now combined into one device. And on top of this, we could upgrade the device from 3G to 4G within days. Of course, the entire platform change took longer, but for the antenna, it took a couple of days to get updated with the additional required bands. The e-antennas have been designed into all types of markets, including, just to mention a few, leading cellular phone companies, handheld systems, leading access points and fixed wireless terminals, wearables, and of course, tier 1 metering and tracking companies. The antennas of TE, they have been approved on all major cellular carriers. And with this, I want to hand over to Matthias.
Thank you, Christian, for the introduction. Compared to TE, Exelonix is a smaller team. Our experiences are in IoT hardware design. So we have a flexible hardware platform that we want to use for the development of different kinds of IoT devices. Most of the changes that we are doing we doing on the embedded software that runs on the device. So we try to have the hardware done as flexible as possible in order to be able to change the behavior of the device just by software. Security is one big issue for IoT at the moment, so we have put a lot of effort into developing a security framework that transmits the IoT data in a safe and encrypted way, and this has to be done with a rather small data rate channel, which is a narrowband IoT. A narrowband IoT is a wireless cellular network that is worldwide available and offers a very low data rate, but also a very low power implementation. So both is of importance because we need to survive this, or we need to have a battery life of longer than a few years with the IoT device. And this is all a very challenging situation. And on the next slide, you will see what our idea of this platform will be. In principle, if you look at the today's devices in the IoT space, they look all different. So they look all, they have all different shapes, all different functionalities that you can build into. The user equipment, the IoT user equipment is always very dedicated to the purpose that they have to serve. And our idea was to transform this kind of, let's say, dedicated device design into platform design that helps us doing multiple multi-purpose devices that we can just change with the by means of software and adapt them to the different use cases that we have. So this was our initial idea, to say build the smartphone for the IoT space. So, and how we've done that with the help of TE, I will come on in the next, or describe in the next few slides. But on the next slide, you will see what are the different stages of a typical IoT project that we are usually doing. So often the customer comes with a certain specification where we do repeat with a certain specification from our side how the device should look like and so on. Often these the initial step is to do a proof of concept, and proof of concept device means prototype devices that you apply in certain environments and test, collect data, test what you can do with the system. Then afterwards, often we have the next step as a product development step, where we try to make out of the proof of concept devices, prototype devices, some more product ready designs, and have that designed in a way that it works perfectly within that particular use case. Then we do mass production of that such IoT device, but this mass production we do regularly with partners. That is not something that we do on our own. And at the end, hopefully we can solve the challenges that our customers gave us, and then we end up with an IoT service that includes not only the devices and the software on the device, but also the backend integration. So the next slide gives you the introduction into the initial challenge that we addressed to TE. What you see here was the performance of our device that we used for tracking. And as you can see, we have a few places where we had a very good transmission working, but you see also it is a drive along a German motorway, and the dot we drove them with that device at a certain speed, and so we didn't change the speed very much. So what we expected was a very regular sampling of the way that we did on the motorway. But what we saw is that in certain places we didn't have a very good transmission. So we probably had coverage problems. We certainly had problems detecting GPS, and at all, it was not a great performance. It was not what the customer was looking for. And we were faced with the question, can we do a better RF performance with standard antennas, or do we have to do our own one? The problem is always you want to have the device as small as possible, and you want the device to perform as good as possible. And therefore, we needed a very drastic improvement on the, I would say, non-function GPS antenna that we had here. That was one thing, and on the other thing, improve the performance of the standard wireless antenna that we had on board. So on the next slide, there's just a summary of the starting point. So we had a small device that with a very small form factor, not a very big ground plane that we can apply there. And also we had Bluetooth as well as wireless communication, cellular communication, as well as GNSS antennas. So let's say 3 antennas in different frequency bands integrated in one device. And we had to make sure that all of them need to perform very well, and all of them has to work and not disturb each other. So we were looking for a partner to do that, and we came across TE at a conference, at the 5G conference, and TE, actually Christian said, he can solve that. He has ideas how to do it, and we were eager to know what they could offer us and what they could do on our purpose. And I would like to hand over to Christian to explain a bit in more detail how he were able to help us.
Thank you very much, Matthias, and we very much appreciated you let us in and started a more intensive communication about the solution It took some time to get to a final solution. First, we had to analyze what's going on. And with this analysis, we found a very typical effect, which we see almost everywhere in the market. I would say in the IoT market, not so much in the cellular smartphone or tablet market, but mainly in IoT market. There was a huge supply of off-the-shelf antennas, and sometimes the data sheets are telling about good results, which are measured in free space on a reference ground plane. And very often in real life, we don't see free space, nor do we see a reference ground plane. If you check on the left side, the data sheet, this cellular antenna required a ground plane of a size according this blue dotted line. And the promise for the efficiency on the right side in the diagram, you see the blue line, which represents the data sheet efficiency of the antenna. Efficiency means how much of the energy will really be radiated out to the air instead of transformed into heat, for example, because of mismatch, because of lossy material, and so on. So the data sheet was showing very, very good efficiency, but on a size which is shown there, the actual size was much smaller. It was 63 by 33 millimeter instead of 130 to 60 millimeter. And the result was kind of not surprising. In the low band, we ended up at like less than 10% efficiency. Size limitations actually caused a very, very severe difference in RF performance. We tried to modify the existing antenna or use something else, but failed. And then we stepped into an approach to apply well-known good practices from smartphone industry. So our entire engineering and manufacturing team, they are really tuned to very good practices of smartphone industry. And we learned during the 20 years plus dealing with those experts, it's all about bandwidth and efficiency. And a lot of benefit can be achieved by using the third dimension of design. So what you see here is a off-the-shelf antenna to the left side. It's kind of a ceramic antenna, SMD element, which is very cost effective, of course, and also very effective to manufacture, very simple. Everything is on a board, like a GNSS antenna over there, the cell antenna over here, a Bluetooth antenna over here. But the sizes would not allow to work them properly. So we checked first with this L-shaped element. This is a laser direct structured three-dimensional antenna element. You may realize there was some space to add for the antenna to the right side. And we were quite happy with the cellular result, with the GNSS result. But overall, the next step brought even better results by adding the Bluetooth antenna to this LDS antenna element. It's all about creating distance to the ground plane, which is giving bandwidth, which is also providing good efficiency, and additional benefit is coming from this 3D design by a better isolation between those antennas. So there was no use if those antennas are coupled very strongly together. The cellular antenna and Bluetooth could have an impact on the GNSS antenna. So we had to care about a good decoupling between those antennas. A holistic approach was necessary. And what did we do? Well, we understood there was a challenge number one, which was the size. You may remember from the previous slide. The challenge number two used to be the real use case. We learned underneath of this PC board, where originally the antenna was located here, oh, well, there's a battery. The battery is full metal, and this would have further taken away efficiency and bandwidth from an antenna which is directly soldered on the PC board. So we had to increase the distance between the board and the battery even further. And on top of this, there was a metal chassis, or could be a metal chassis, underneath of the tracking device. Now we went into a very intensive investigation. We took the metal device as an example. The gray piece over here should represent this use case, metal use case. We put the tracking device represented by those orange boxes either to the corner or to the edges, the short edge, the long edge, or in the center. And we also applied different heights between the tracking device and the ground plane. It was amazing to see how much the impact was on the RF performance. We found, of course, P2 and H1, they presented the most challenging use cases, and we took them as a reference, as a benchmark to design the antenna properly, to give Exelonix a good way to keep margin for any other use case and not run into trouble when the use case would be in accordance to H1 and P2 positions. Now, this is again a summary of the first concept, the LDS block antenna L shape, which had the LTE antenna and a GNSS antenna on there. I want to highlight one thing. There were many IoT devices equipped with, for example, LoRa or Sigfox single frequency band applications. Does not require a great deal of certification, so it's more a simple approach. LTE, narrowband IoT, and CAT M1 are very much different because they require, even if they are called narrowband, they require wideband antennas which operate from, as you can see over here, 698 to 2100 megahertz. Multibands need to be covered and certification is required. So for those tiny small devices, which are more or less the form factor of a smartphone, it is a benefit to work with folks who are really, grown up with the smartphone industry to copy paste those well-known good practices. So this is the final design. It's finally a U-shaped antenna. Those are hooks over here, which go directly onto the board. You may ask how to connect this antenna to the PC board. The first attempt was soldering cables. So we could solder cables onto those antenna feed points if needed. But the most straightforward and repeatable process for mass production is, again, a technology that was taken from smartphone industry. It is connecting those antenna feeds for each antenna by spring clips. Those spring clips, they are SMD components. They get soldered to the PC board. And as a final achievement, the block antenna had all antennas integrated. It had a maximum ground distance. It was easy to assemble for mass production, and it gave the Exelonix team some more of a tolerance window for other mechanical elements to assemble. Now, this is, again, a picture of those spring clips. The antenna itself, we had to hide the pattern, unfortunately, so the product is not yet finally released. So those patterns, the cell antenna works with Metaspan technology. This is a TE patented antenna pattern technology providing a good bandwidth at a smaller form factor. It is a combination of left hand and right hand feeding the antenna. This one, the GNSS antenna, that's a PFA antenna. The Bluetooth antenna is a PFA antenna as well. And the snap-on feature provides an easy to assemble methodology for scalability in mass production. Now let's look to the results. Well, the brown line actually represents where we are coming from. At 700 megahertz, there was almost nothing left on efficiency. Means most of the RF energy was transformed into heat, got lost, or not lost, got transferred to be clear. Now the blue line represents the final device. In the lower frequencies, so we could achieve at least 20%. Those vertical lines, they represent the band limits. Those ones, this is high band, this is low band. And this horizontal line represents the certification limit. The aim was to be better than 20% with the efficiency of those antennas, which is resulting in long battery life and a very good connectivity over time. With this, I want to hand over for a conclusion to Matthias.
Yeah, thank you, Christian. So now you see clearly on the, if you look at the pictures, so the left-hand side is where we came from with the outage of between the, or a lot of places where we had outages between the dots. And the right-hand side was the same track again with a different, with a new antenna right now. And what we saw is a wonderful improvement and almost no errors anymore, so almost no outage. And I have to say, the biggest challenge on our way there was especially the low frequencies that we had to use for the narrowband IoT. Narrowband IoT in Germany uses the frequency band within the 800 megahertz frequency band, and this frequency band is good for coverage because you can cover the attenuation of the signal is not as strong as it would be for higher frequencies. But on the other side, if you have a small device, and IoT devices tend to be small, if you have a small device, then your ground plane is probably not big enough and your antenna is probably not big enough to have a superior performance. And therefore, you have to do some very good RF design. And this is where with the help of TE, we had a strong partner within TE to overcome these limitations. So therefore, this one resulted not only in a superior performance within the tracking performance, but also it increased the battery life because we were able to find the position faster than with the old antenna setting, because the GNSS performance also improved along with the cellular performance. At the end, we got very good feedback also from our customers for the improvement that we did from the proof of concept phase to the product phase, and therefore that is all you can think of as a company that's doing IoT devices, making your customers happier with the actual product than they were with the proof of concept version. So therefore, this turned out to be a very successful step. So coming to the next slide, we want to sum up the findings. And maybe Christian can take over because a lot of them, the findings were within the respect of the RF performance.
Thank you, Matthias. And I want to say thank you to you and the entire team for a very intensive collaboration. So you mentioned before, you're a much smaller company than TE, but actually agility matters, not so much size. And so together we could form a very, very strong team and a smooth approach to final certification. And there were some conclusions which are valid for multiple IoT applications, which we can draw from this experience for antenna implementation. It's very good to think about the antenna pretty soon. Try to understand how the antenna need to perform in the worst case situations. Take this as a benchmark. Try to understand datasheet recommendations in a proper way. So read the footnotes. That can help a lot. And in many cases, when the footnote or the datasheet requirements cannot be met, connect with RF experts who can help to make it work. And test in particular efficiency, which is similar from which is different from just measuring return loss by network analyzer. For efficiency, there was a chamber needed. So there were communications analyzers needed to test the TIP, the total isotropic sensitivity, and the TRP, which stands for the total radiated power. There was a little bit more experience and equipment needed. TE can do all this, and in a very, very short time frame, and with a test, it's really a severe requirement to exclude mistakes and provide a first-time right solution. You can't cheat physics with any software or goodwill. I think, Matthias, you made this statement once, and I'm very happy you made this, because this is very much true. So we are trying to exceed expectations in time to market and end user satisfaction, not just with the antennas, but also with related connectors, sensors, board level shielding, and other components which mechanically interconnect devices from the IoT. So this is what our customers can expect from TE. First, it's a baseline evaluation, of course, to see where we are. Tuning standard antenna solutions from catalog. There were a couple of thousand antennas available directly from the catalog without any kind of customization. We could tune those, or if they are not applicable, design customer-specific antenna solutions. Where do we know it's working good enough? Well, run efficiency optimization, coexistence optimization. Coexistence means GNSS and cellular and Bluetooth and Wi-Fi might have to work simultaneously, and we need to ensure with a proper antenna setup, those antennas, they are not disturbing each other too much. They will disturb anyway, but we can help to make this disturbance the minimum. There was an active and passive antenna performance test capability, as well as surface absorption rate optimization and radiation pattern optimization if that's needed. And with all those functions and different items, design for manufacturing is very high on the thinking of the team of engineers. The fanciest, most nicest solution also have to be manufactured in mass production. And sometimes, it's a problem to get this one up and running. So for antenna design, system integration, and use case adoption, RF is TE is a very good partner based on long-term experience and a couple of 10,000 use cases and projects which have been done successfully. Here are some key takeaways and success factors. Actually, it's a solution know-how. It's not so much the equipment that is standing around, it's the people who can manage the equipment, but feed them correctly, read and understand the outcome of the equipment, and turn them into antenna patterns or antenna solutions which finally work. Then a good first-time right solution will come out of this. So test capability, there were multiple test locations around the globe, in America, in EMEA, in Asia, which can do a variety of different passive and active tests for antennas. There was in-house manufacturing, so most of the antennas are manufactured in-house, no matter whether they are embedded antennas or external antennas. Recently acquired external antennas from Laird, added a great deal of new portfolio, which we haven't had before. And overall, this will help time to market. This will help to be not too late. I remember a customer told us and we want to compose well-known technologies and components to create something amazing. So RF will probably not change in the next couple of years, as it hasn't changed the past 20, 30, 40, 50 years. And together, we would like to provide the competitive advantage to make devices successful in the market. With this, I would like to hand over to Bianca.
Thank you, Christian. And thank you, everyone, for joining today's call. If you would like the opportunity to connect with us further, please visit us at te.com or exelonix.com. As we move forward onto the next slide, that concludes the presentation portion of today's webinar and today's call.